In this flip class video, we're going to talk about velocity and its relation to tangent lines. So let's start with a practical example here. So in the 2008 Olympics held in Beijing, China, Usain Bolt broke the 100-meter dash record. So here's a picture of him crossing the finish line. You can also click on the link here if you'd like to see an actual YouTube video of him winning this race. So suppose we were interested in his speed at various points during the race. One thing we can do is we can take measurements at various times and various distances to see how far he's traveled over those distances. So if we do that, we can ask a computer to model the data points we have. And for this, I went ahead and did this and fit it with a parabola. So it's not so important how the computer does that, just that it does do it. And this equation here, S of t, which is the same thing as d of t, is our distance function for telling, if I input a time t, this will tell us how far Usain Bolt has traveled in that amount of time. T here is measured in seconds, and the distance is given out in meters. So we can see, for instance, if I'm interested in 6 seconds, I go up here to 6, go over to this, and it looks about like 58 or something for the meter. So that's what this function is telling us here. So, like I said, we're interested in a particular at any particular time during the race. Let's see what his speed is at that time. So let's focus on the time t equals 6 seconds. So we know Usain Bolt's not traveling at a constant speed because he starts from not moving at all and then accelerates as the race goes on. However, if we know someone is traveling at a constant rate, then we define their speed in that case to be the distance traveled over the time it took to travel that amount of distance. So we can't use that exactly for Usain Bolt, but we can say if we measure the distance traveled over some short time interval, his speed's probably not changing much over a very short time interval. So we can use that to help us estimate his speed at any particular time. So for this, we'll use the average speed. So for the average speed, say between time t equals t0 and time t equals t1, we'll take d of t1 minus d of t2, so that's the distance traveled in that time, because if you start off the travel d of t0 and then you go a little bit more to get to d of t1, so the difference between those is the distance traveled over that interval, and then we're dividing by t1 minus t2, which is the amount of time over that interval. So that gives the average speed over the interval. And the idea here is going to be that if we let that T1 and T2 be close to each other, then the average speed is going to be a pretty good approximation for the speed at a particular point. In our case, T equals 6. So let's suppose we took some measurements during the race, and we measured how far he had traveled after 5.9 seconds, at 6 seconds, and 6.1 seconds. And we get these values here in meters of 53.77, 54.94, and 56.12 for the distances Usain Bolt had traveled in those time periods. So we can use these to get his average speed. So suppose we look at these first two. So the difference of how far he's traveled from 5.9 seconds to 6 seconds. So the actual speed at t equals 6, this is approximately equal to the average speed. So it's not exactly equal to, it's just approximate there. It's important that we're careful with what things are equal and what things are approximate. So I look at the distance traveled after 6 seconds minus the distance traveled after 5.9 seconds, divide by the time difference. And when we do this and we plug in our numbers from our table, we get about 11.75 meters per second. So one thing to note here is we can guess that the speed is going to be measured in meters per second. If we weren't sure of that, we could look back at our equation to get this. So notice that the top part here is the distances traveled. So distance is measured in meters for our case. And the bottom part is the time. So the time is measured in seconds. So you can think of this as meters per second. So that's where our units are coming from out of our equation. So that gave us an estimate if we use the time right before 6 and 6. We can also use 6 and the time right after 6. We can also use the time before and the time after. For now, we'll just go ahead and use 6 and 6.1 to get another estimate. So do the same process with the 6.1 and 6. In this case, we get 11.82 meters per second approximately. So if we want to get a better estimate, we can go ahead and average the two answers we got. And if we average the 11.75 and the 11.82, we get about 11.78 meters per second as our estimate for Usain Bolt's speed after 6 seconds of the race. Now, if we want to improve this estimate, what we'll do is we would take a better measurement. So we would measure a little more precisely and maybe look at 1/100th of a second before 6 seconds and 100 second after 6 seconds. And if we do this, we get the values 54.82, 54.94 again, same thing as before, and then 55.06 for at 6.01 seconds. And now we just do the same procedure and we look at the average speed over those times to estimate our actual speed. So if we do this for the one right before 6 seconds, we get about 11.78 meters per second. And we can do the same thing with the 6 and the 6.01, and we get 11.79 meters per second. So if we average that 11.78 and then 11.79 together, we get about 11.785 meters per second for Usain Bolt's speed at 6 seconds into the race. So we could continue to get closer and closer measurements and get a better estimate by taking the interval surrounding the 6. If we want to do a little bit better, we could do 5.999 and 6.001. And that would give us a better estimate. We could keep doing this, and the closer we get for our interval, the shorter length of our interval around 6, the better our estimate for the speed is going to be by using the average speed. So we might also like to say, okay, well, we understand what's happening in terms of getting estimating the speed from the average speed, getting the data from a table, but what is this telling us geometrically about that graph that we started with Usain Bolt's distance in terms of the time into the race? So the function modeling his distance traveled was a quadratic, but it was somewhat flat. So for this, let's suppose our distance function instead is e raised to the t, so it's a bit curvier. This will help show what the geometry is giving us a little bit better, having a little bit stronger curve in our graph. So for this case, let's suppose I want to estimate what the velocity is at t equals 1 and see what this means geometrically. So we know that we can estimate the velocity at t equals 1 by using the average speeds over intervals containing 1. So where we have a and b, with a less than or equal to 1 and b is less than or equal to 1. And we can't have a and b are both equal to 1. We could have either of them equal 1 or neither equal to 1. But we do want to take the distance between b and a to be somewhat small to get a good estimate. So let's see what these average velocities or average speeds are meaning geometrically. So if I look at 2 points here, so I can start with the point 0, 1. It's a little tricky here. The t is 0. Notice this is 1, and we're not starting the graph at 0, 0. So notice each of these has a distance of 1 between them. So this is actually the point here, 0, 1. And then I have my graph, y equals e to the t. Notice I cross it up here again at 2e squared. So that red line is the line that passes between those 2 points. And now if I look at the quantity change in y over change in x here, d2 minus d0 over 2 minus 0, well, this gives me about 3.19. But the point is this is the slope of that red line that we've drawn there. But it's also, from what we've done before, the average speed over the interval from t equals 0 to t equals 1. So a line like this, where it goes through 2 points of the graph, is often referred to as a secant line. So the slope of the secant line here is giving us the average speed over the interval, where the interval is where the points are touching the graph. So from here, from 0 to 2. So in order to get a better approximation, we can see this isn't really a great approximation at 1 because 0 and 2 are pretty far away from 1. So this is a pretty big interval. compared to what we were looking to before, where we were like 100th on each side of what we were interested in. So we could ask, as we let that interval get smaller so the A and B values get closer together, what happens to the graph? So here's a little animation that shows us this. So you can see as those get closer to 1, that line is moving down towards the graph, getting closer and closer to touching it at only 1 point. When it touches it at only 1 point, that's called the tangent line. So if we look at this, we can see the lines, those secant lines, are becoming closer to the tangent line at t equals 1. And so if we look at that, here's our graph of what's going on, and we can see those red lines are getting closer to that green tangent line. Now remember, the slopes of these red lines are our average speeds over those intervals. And we saw before that as those intervals got smaller, those average speeds gave us a better and better approximation for the velocity at the particular point we were looking at. So geometrically, we can see, since the slopes of the secant lines are the average speeds, and they're getting closer to the tangent line, that would tell us that the slope of the tangent line should be the speed at t equals 1. So that's how the geometry relates to the tables and equations from before.